Okay, two main topics we're going to deal with today are standard deviation and the 68, 95, 99.7 rule. But before we get to those, we're going to do a little bit of a review of order of operations. Remember, order of operations, we describe that as please excuse my dear Aunt Sally. And what we're talking about here is anything that's in parentheses gets done first. If there are exponents, they get taken care of next. Multiplication and division are next. They're equals in this hierarchy, so we would do those left to right. And then finally, addition and subtraction that are also equals that we would do from left to right. As we look at this expression we've been given, we can see that we have some subtraction, we've got addition, we've got exponents, and we have parentheses all over the place. Since we have parentheses, and there are things to do inside those parentheses, that's what we're going to do first. So we're going to simplify the things that are inside the parentheses. Here we have 4 minus 8. That'll be negative 4. And 11 minus 8 will be 3. Just as a little reminder, you might be thinking, do you still need these parentheses? Because you've done the subtraction. There's nothing left to do inside the parentheses. Do you still need to keep those parentheses? And I'm going to say yes, and there's a reason for that. You may remember back to algebra somewhere along the way, and if you don't, it's okay. The idea of negative 4 squared compared to negative 4 squared. And the parentheses mean something there. A lot of times parentheses, we just kind of use them out of convenience to show multiplication and to keep things organized. But here, the parentheses really do mean something. And what's going on here is this. In this setup down here, the only thing getting squared is the 4. And then the negative just comes along for the ride. So this would be 4 times 4, and the negative just comes along with it. And so we wind up with an answer of negative 16. In contrast to that, the one up above, those parentheses mean something for us. They say everything inside these parentheses gets squared. And so what that means is that's negative 4 times negative 4, which ends up with a positive 16. And so the parentheses definitely have a meaning here. And in the problems we're going to see, we're going to be working with this structure here. We're going to keep those parentheses around our number because we want to square everything that's inside those parentheses. And so negative 4 times negative 4 results in a positive 16. Slightly different from what we would see down here, and this is the type that we are going to be concerned with in what we're going to study today. Clean that off, and we'll go ahead and finish this up now. So that negative 4 squared, that's negative 4 times negative 4 is positive 16. And 3 times 3 would be 9. And then finishing it off, we end up with 25. We've simplified this to be 25. We used order of operations to do what's in the parentheses first, then exponents, and then we did the addition. And a key here is keep those parentheses because we want everything that's in there to get squared. Where we're going to see this type of work is when we're finding what's called the standard deviation. The standard deviation tells us how spread out a data set is. Are the data points really close together, or are they really spread out? The standard deviation is sort of a measure of how spread out they really are. Logic would point you in the right direction here. The higher standard deviation that a data set has, the more spread out the data points are. So if we had one data set with a standard deviation of 9 and another data set with a standard deviation of 11, it's the one with the standard deviation of 11 would be more spread out. How this might be valuable at this point is just, let's say if I had 2 different sections of Math 120E and I was looking at their exam scores and I took a look at the standard deviation for each class, and one class had a relatively small standard deviation, and the other one had a relatively high standard deviation. What that would tell me is one of the class's scores were more consistent. They were all kind of together. And the other class were more spread out. I had some really high ones, some really low ones. They're all over the place. And that's a way that standard deviation can be useful in comparing two data sets. Which one is more spread out than the other can be determined by looking at standard deviation. Calculating standard deviation is done by using a formula, and it's this formula right here. At first glance, it's perfectly fine to be a little intimidated by that formula. There's a whole lot going on in there. We're going to take a little time to sort of take some of the mystery away. The first thing you might notice over here on the very left-hand side is this symbol. And what that symbol is, it's the Greek letter sigma. It's a lowercase Greek letter sigma. Kind of nice that it starts with an S, because what that represents is standard deviation. So that sigma right there is standard deviation. Essentially, this is the formula to find the standard deviation. There's another symbol in there that looks pretty unusual, and it's this one here. And it looks like a lowercase cursive u. And it's actually the Greek letter mu, which is pronounced like that, mu. It's the lowercase Greek letter mu, and what that is, that's going to be our mean of our data set. And we see that appears in several different places. So at this point, sigma here is just a symbol that represents our standard deviation. And then mu, this symbol, just represents the mean of the data set. Okay, that's fine. I'm going to calculate standard deviation. I know what the mean is. So far, so good. This n that's underneath the division bar there, that's just the number of data points. So if you happen to have 7 data points in your data set, then that's going to be 7. It's just the number of data points. All right, we've taken care of most of this. What we have left is this x with a little 1, x with a little 2, all the way down to x with a little n. What those are our individual data points. Let's talk about those names for just a second. This, for example, x with a little 1 next to it. What that is, the way that we would formally describe that is x with a subscript of 1. X with a subscript of 1. That's a lot to say. Even x subscript 1 is a lot to say. So we're going to abbreviate that, and we're going to call this x sub 1. So if you hear me say x sub 1, I'm not saying x of 1. It's x sub 1, which is shortcut for x with a subscript of 1. And what that x with a subscript of 1 is, that is our first data point. X with a subscript of 2, x sub 2, that's our second data point. And then every one of these gets an index. If we have a third data point, it would be x sub 3. And we keep going till we get to the very last one. If I have 7 data points, then this x sub n would be x sub 7, because that's the last one, because this n tells me how many data points there are. So if there are 7 data points, I'm going to keep going till I get to x sub 7. It just tells me each data point has this index to go with it. X sub 1 is the first one, x sub 2 is the second one, x sub 3 is the third one, and so on till we get to the very last one. And I've made quite a mess of it, but that's the formula. And that's every individual piece of the formula for standard deviation. We've got our data points and our mean, the number of data points. Those are the things we're going to be working with. So at first it looks a little daunting, but honestly, once we start putting numbers in there, which we're going to do in just a second, you're going to see that it's actually probably much more comfortable for you than you thought it might be. Let's take a look at one. Find the standard deviation for the data set 42, 47, 61. Your first thought here might be, there's only 3 data points. I mean, come on, how many data sets really only have 3 data points? And you'd be exactly right. Not very many data sets have only 3 data points. But for our purposes in finding standard deviation, I want to know if you can use this formula. And I don't need to have 12 data points in the data set to know whether or not you can use the formula. In fact, that might be a form of torture to have you do this with 12 data points. So we're going to keep the data sets we work with related to finding standard deviation. We're going to keep those data sets really small so that it's not an overwhelming amount of calculation. All right, so got the formula there, and I'm going to start plugging stuff in here and see how this goes. Oh, well, you know what? It would be nice if I kind of knew what everything I'm going to plug in was before I start just throwing numbers around. So you know what? I'm going to give these names. This is x sub 1, my first data point, x sub 2, my second data point, and x sub 3, my third data point. There's only 3 data points, so I know that n's going to be 3. At this point, I already know what I'm plugging in here, 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 and here. The only thing left that I don't know that I need to plug in is the mean. So let's find that. The mean will be, let's see, I need to add them up and divide by how many there are. 42 plus 47 plus 61 over 3. All right. 42 plus 47 plus 61 is 150 over 3, which is just 50. Now I know everything that I need to plug into this formula to calculate standard deviation. So here goes. If you see anything that you're not sure of where it came from, let me know. So my standard deviation here is going to be, and I never make this long enough, so I'm going to try to make it super long. All right. X sub 1, which is my first data point, 42, minus the mean, which I just found to be 50, squared, plus x sub 2, which is 47, minus the mean, squared. And I keep doing this till I get to the very last data point. Well, I'll only have one more, so I'm already at the last data point. And that'll be 61 minus the mean, squared. Almost me. And then the whole thing is divided by the number of data points there are, which is 3. I've plugged everything in. Now I just need to simplify it. When simplifying this, the last thing we're going to do is worry about this square root. That's going to be last. I have this long division bar here, and anytime I have a division bar like that, order of operations with the division bar tells me do everything on top, do everything on the bottom, and divide last. So I just need to clean up the numerator of that fraction that's under there. So let's start working on that. Okay, standard deviation will be, and your first thought might be, this is going to be a real grind. Honestly, it cleans up a lot faster than you might think. 42 minus 50 is going to be negative 8. 47 minus 50 is negative 3. 61 minus 50 is 11. And that's divided by 3. And, you know, it's already shrunken down to something pretty manageable pretty quickly. Now we'll go ahead and do that squaring. And just as a reminder, we're squaring everything inside those parentheses. So negative 8 times negative 8 will be positive 64. Negative 3 times negative 3 will be positive 9. And 11 times 11 will be 121. Let me know if you see anything that feels like it's out of left field, you're not sure where it came from. We're going to continue with our simplifying here. Standard deviation will be, let's see, I need to add those up. 64 plus 9 plus 121 is 194 over 3. I've done everything in the numerator. Now I can divide. And when I divide that 194 divided by 3, I get 64.666666, and that keeps going. I'm not quite done yet, though, and this is an easy step to forget because we kind of got a number. You know, we had all of these expressions we had to simplify and then square them and then add them together. Fighting with my pencil again. And then divide, and now we have this number right here, and it feels like we ought to be done. But we have one more step to do. We still have to take that square root. You should have a square root button, might have a little 2 next to it so that we can take the square root of that 64.66666. We'll leave it sitting on our calculator. We'll go ahead and take the square root of it. And we weren't told where to round in this one, but let's just round to the nearest hundredth. That's generally a nice place. We'll round to the nearest hundredth, and our standard deviation for this data set will be 8.04. I want to talk back through what we did there and then have you try one. So the first thing we did, it said find the standard deviation for this data set. It means I'm going to use this formula, and I'm going to be more comfortable with that formula if I know exactly what to plug in where. So I'm going to take a minute and label my data points as x sub 1, x sub 2, x sub 3. Since I have 3 data points, n is going to equal 3. And the other thing that I need to plug in here besides data points and the mean, or excuse me, data points and the number of data points is the mean. So I'm going to take a second and calculate the mean, and I found out that the mean was 50. Now I'm going to go start plugging things in over here, and I get x sub 1 minus the mean squared plus x sub 2 minus the mean squared plus x sub 3 minus the mean squared, all divided by the number of data points. Now I just need to simplify this thing. Order of operations tells me do everything on top, do everything on the bottom, divide last. So to simplify everything on top, I need to follow order of operations. I'm going to subtract inside my parentheses. Then I'm going to do the squaring of each of those. Finally, I'm going to add the 3 numbers that are in the numerator to get to here. Finally, I'm at a place where I can divide, and then I absolutely don't want to forget that last step of taking the square root. This gives me the standard deviation of the data set. It gives me an idea of how spread out it is, maybe compared to another data set that I might find the mean or find the standard deviation for. I won't go into too much detail on this, but I do sort of want to highlight the idea of what we're doing. What we're doing here is how far is each data point from the mean? How far is each data point from the mean? Because that's how we can figure out how spread out it is. How far is it from the mean? That's what those subtractions do. And then the reason for the squaring here is, well, some of my how far from the means are negative numbers, and some of them are positive numbers. I don't want to just add those up, because if you look here, this -8, -3, and 11, if I added those, they would wind up at 0, indicating my data set's not spread out at all, which that's not true. The numbers aren't all the same. So the reason we square is to make sure it's all positive, because we're talking about distance from the mean, and if we're talking about distances, we want positive numbers. Squaring also adds some emphasis to the numbers that are further away. You know, by squaring this 8, it blows it up to 64. Squaring a 3, it only goes to 9. So numbers that are further away from the mean really get a big number in there when we go to calculate standard deviation. Since we did that squaring at this point, we've got to undo that. And that's why our very last step is to take the square root. I'm not going to ask you to explain why the standard deviation formula looks like it does, but in case you were curious, essentially it's a measure of how far are your data points from the mean. That's what it is. All right. Are there questions about what we did here before I have you try calculating a standard deviation? Excellent. Here goes. Find the standard deviation to the nearest hundredth for that data set, 7, 13, 22. I know there's a lot to do here, so I'll give you a little time on this one to find the standard deviation for that data set. I will tell you that computationally, this is um, this is as challenging as we're going to get. So if you can find the standard deviation for that data set comfortably, I don't think any of the other calculations we do today will give you trouble. Just be patient and careful as you go through this step by step. I think it helps if you identify what needs to get plugged in where at the beginning, but you don't have to if you're comfortable just sort of, you know, throwing everything in there to the formula. This is always one of those types of things that if somebody happens to be looking over your shoulder while you're doing your homework, it's very impressive. I mean, and it just is. That's just how it is. You know, not only does it look impressive, but it is impressive. And this is the standard deviation calculation won't be a huge point of emphasis for us, but it is something you can expect to see when you're practicing problems and homework, quizzes. You know, this is something that I think it's, you know, it's a somewhat challenging but very manageable thing for you to be able to calculate. I was thinking we go about another minute on this. If you want more time, let me know. All right, let's take a look at how we're doing. Unanimous. Outstanding. That is excellent. Very good. I've kind of had in my head that we're doing really well with most of the content, and it seems to be the case here. I'm going to go ahead and go through this, but given the results of the poll, I may do it relatively quickly. If you see anything you're not sure of, make sure you ask. So I'm going to go ahead and label these as x sub 1, x sub 2, x sub 3. I know my number of data points is 3, and I know I'm going to need the mean, which will be 7 plus 13 plus 22 over 3. So let's see here. 7 plus 13 plus 22 is 42 over 3, which is 14. Okay, got everything I need. I can start plugging in. So we'll have standard deviation will be square root of the data point minus the mean squared plus next data point minus the mean squared plus next data point minus the mean squared all over 3. Righty, now we'll do our subtractions. So let's see here. When I do my subtractions, I'll have negative 7 squared plus negative 1 squared plus 8 squared all over 3. Squaring gives us negative 7 times negative 7 is 49. 1 times 1 is 1, and 8 times 8 is 64 all over 3. We'll go ahead and add those together. 49 plus 1 plus 64 is 114 over 3. 2 more steps to go. We're going to divide 114 divided by 3 and get 38. And this is the first time we've arrived at a number to be an answer, but given the poll, none of you really forgot the idea that we still need to take the square root. And when we take that square root and round to the nearest hundredth, we end up with a standard deviation of 6.16. Excellent work on the poll. Excellent work on that concept. I'm thrilled. This is something that can be challenging, and you did a great job with it. Please let me know if you have any questions about anything that we did there. But I feel pretty confident that we can go forward off of standard deviation now. Where we're going to see the real value of standard deviation, and there is value in how spread out is a data set compared to another data set. The real value we're going to see with standard deviation is coming up soon. The normal curve. This is sort of our other big topic for today. On Tuesday, we talked about histograms and how those are bar graphs that are drawn without any spaces between the bars. And what I've done here is created a histogram, there's not any spaces between those bars really. I just put the spaces in there so that you could see that there were actual bars rather than it looking like just a big blue blob. So imagine there's no spaces between those bars and they all press up against each other. And if I have a data set that's like that, where I've made a histogram and there's no space between the bars and that's the shape that it makes, something I can do is I can put a point in the middle of the top of each one of these bars and then connect those dots to make a curve. And then after I've made my curve, I can take the bars away. And instead of looking at this as a whole bunch of individual bars, we can look at it as a curve that has all of those bars underneath it. That's our normal curve. Some things that are true about data that fits the normal curve. When we have data that looks like this, when we make a histogram, there are some truths about it. Right smack in the middle, that's where the mean is going to go. So the mean's going to be right smack dab in the middle. The median would be exactly in the middle also. But the mean is going to be right in the middle. And what you can see from this data set as we get further away from the mean, the number of data points gets smaller and smaller and smaller. They taper off as we get further away from the mean. And that happens on the positive side. It also happens on the negative side, below the mean. It happens above the mean. The number of data points there are gets less and less as we get further from the mean. And to the left of the mean, the number of data points gets smaller and smaller as we get further away from the mean. And that's going to be true for any data that we call normally distributed. So for data that is normally distributed, meaning that if we make the histogram, it looks like this, and then we can take the bars away and just use the curve instead. The mean is going to be exactly in the middle, and the number of data points tapers off as you get further away from the mean on both sides. It's going to be symmetric about the mean also. Some data sets that are normally distributed are standardized test scores would be an example of normally distributed data. If you think about the millions of people that take a standardized test, there's going to be a mean score right here in the middle. A lot of the people's scores are going to be close to the mean. And as we get further away from the mean, there's going to be less and less. There's going to be very few people out here with a really high score. And there's going to be very few people down here with a really low score. It fits the normal curve in that most of the scores are in the middle, and the further you get from the mean, the number of scores tapers off, and that's in both directions. Something else that fits the normal curve would be the weights of newborn babies. There's going to be a mean right in the middle. Most babies are going to be close to the mean, but there are going to be fewer and fewer as you get further away, and somewhere out here is going to be a very small number of really heavy babies, and similarly a very small number of really light babies. And something else that has come up in other examples for us, the lifespan of batteries. Most of the batteries are going to be in here close to the mean. As we get further from the mean, there's going to be some batteries that lasted a really long time. And then there's going to be some that lasted not very long at all, but there shouldn't be very many of those. And so most of the data points close to the mean, as you get further from the mean, they taper off. And that's how normally distributed data works. Okay, we talked standard deviation. We talked about the normal curve. Now let's put those things together using the standard deviation with the normal curve. So we've got this picture down here that is our normal curve, and hopefully you recognize that symbol for being the mean. That's right smack in the middle of our normal curve. And what we're going to do is we are going to section off all of this space that's under the normal curve, And the way that we're going to section it off is by using the standard deviation. Here's our mean, and we are going to go one standard deviation above the mean. So if you think about this for a minute, we're at the mean, we're going to add one standard deviation to it. We're one standard deviation above the mean. Now, we don't have any numbers to plug in here yet, and honestly, I think this will all really come into focus for you when we start using numbers. But strictly from an abstract sense, we're going to draw a line at one standard deviation above the mean. We're going to draw another at 2 standard deviations above the mean, and we're going to draw another at 3 standard deviations above the mean. We're going to do the same thing below the mean. This will be 1 standard deviation less than the mean. So 1 standard deviation below the mean, we're going to draw a line. 2 standard deviations below the mean, we're going to draw a line, and 3 standard deviations below the mean, we're going to draw a line. If you're thinking, what good's that going to do? It's a perfectly reasonable thing to be thinking for right now, and I'm going to show you. It's because of something called the 68, 95, 99.7 rule. This is also known as the empirical rule. So if you see solve this problem using the empirical rule, what it's talking about is this rule right here, the 68, 95, 99.7 rule. And what that tells us, what that 68, 95, 99.7 rule tells us is when we have data that is normal, meaning a graph of it makes this shape right here. When we have data that is normal, the 68, 95, 99.7 rule tells us 68% of the data is between 1 standard deviation below and 1 standard deviation above the mean. If we're looking at just this part underneath that curve, that's where 68% of the data has to be. If it's normally distributed data, this is an absolute fact. 68% of the data is between 1 standard deviation below and 1 standard deviation above the mean. The 68, 95, 99.7 rule tells us that 95% of the data is between 2 standard deviations below and 2 standard deviations above the mean. So if we start at the mean and we go over here 2 standard deviations above and 2 standard deviations below, and we're looking at this chunk right here, this 68, 95, 99.7 rule tells us 95% of the data points are in there between 2 standard deviations above and 2 standard deviations below the mean. And then you know what's coming next. What's coming next is, it's called the 68, 95, 99.7 rule. If we go out here to 3 standard deviations above and 3 standard deviations below, that's where 99.7% of the data is. Almost all of it. Not all of it, but almost all of it. 99.7%. One thing that I want to make sure to point out is there is nowhere on here where we can say 100% of the data lies. We're never going to make a claim about 100% of the data. If you think about this in terms of battery life, 99.7 of those batteries are going to be between 3 standard deviations below and 3 standard deviations above. That's true. But then there's that one battery that just wouldn't die. It just kept going. It lasted forever. It's way the heck out here. We can't say 100% because there are outliers that are way over here or way over here. So we're never going to say 100%. What we can say, because of the empirical rule, is 68% of the data is within 1 standard deviation of the mean. And then we can say that 95% of the data is within 2 standard deviations of the mean. And then finally, 99.7% is within 3 standard deviations of the mean. But there's nowhere where we can assert 100% of the data because you can have crazy outliers. And in order to account for the fact that those exist, 99.7 is as high as we're going to go. We can take this one step further to get to the most useful picture you're going to have for section 3.5, and that's this one. because the empirical rule tells us 68, 95, 99.7, we can break down every one of these individual slices into the amount of data that's in there. What we've done here is taken the 68, 95, 99.7 rule and applied it to every region under the curve. We know 68% of the data is within one standard deviation of the mean. And we know the normal curve is symmetric. So that means there's 34 in here and there's 34 in here. Has to be. If it's normal data, that's where the data points are. And then, okay, well, if I go out to 2 standard deviations, that's where 95% of the data is. And so between 95 and 68, that would be an additional 27% of the data. So 13.5% is in this piece and 13.5% is in this piece. And so on. 2.35% is here and here. And then those crazy outliers we talked about that are beyond 3 standard deviations above and below the mean, that's 0.15% of the data that is out there. This picture is going to be really, really valuable for us as we solve problems related to the normal curve. It's on page 250 of your book, and it's going to be really important for you as we go through solving problems. You're going to see that as we go through the rest of the problems that we work on today. We're going to use this picture, and the idea behind the 68, 95, 99.7 rule that gave us this picture to answer questions. All right, let's take a look at the types of questions we're going to be able to answer related to the normal curve. And I promised you that I would put some numbers down here, and that's what we're going to do next. $2,000 students took a standardized test that had a mean of 250 and a standard deviation of 50. So notice, we've been given the mean and the standard deviation. That's all we need to be able to answer these questions is what is the mean? What is the standard deviation? Now I'm ready to answer a whole bunch of questions. Here's how we're going to do that. And I'm not even going to look at these questions yet. The first thing I just want to talk to you about is the mean and standard deviation. So we draw our normal curve, and our mean is 250. And I know the standard deviation is 50. Okay, so if I want to go 1 standard deviation above the mean, that's going to be whatever my mean is plus 1 standard deviation. So it's 250 plus 50. That is where a score of 300 on this test would go. I'm going to ask you the next one. I'm going to draw another line over here that's 2 standard deviations above the mean. What number needs to go down there? What would be another standard deviation above the mean? I went from 250 to 300. What's going to be next? If I'm going to be another standard deviation above the mean, what number needs to go down there? And the more of you that tell me, the better, because then I know where we are. Excellent, Ashley, Arian, perfect, 350. Because this is 1 standard deviation above the mean. Now I need to be another standard deviation away. So that's another 50. So this next one is going to be at 350. And then to be a 3rd standard deviation above the mean, that's going to be 400. Okay, what's going to go over here? 1 standard deviation below the mean. What number is going to go in there? Excellent, Ashley. Very good. And Arian, I'm confident you know too. It's going to be one of these below the mean. So 50 below the mean. So that's going to be 200. And then I'll go 50 more and be at 150, and 50 more and be at 100. So essentially what I've set up here is I've got my mean, and I've got 1 standard deviation above the mean, 2 standard deviations above the mean, 3 standard deviations above the mean. I also draw on the back side and have 1 standard deviation below, 2 standard deviations below, 3 standard deviations below. And those labels, along with this picture, are going to help me answer whatever questions get thrown my way. And in fact, I'm going to go ahead and just use this picture. 250 was our mean. 50 was our standard deviation. And so that'd be 200, 150, and 100. Before we start answering any questions, I want to make sure we're all comfortable with those numbers and where they came from. The idea that 250 was our mean, we were given that in the problem. We were also given that 50 was our standard deviation. So we go up 50 to get this number. We go up 50 more to get this number, and we go up 50 more to get this number. On the left side, we'll go down 50 to get this number, down 50 more to get this number, and down 50 more to get this number. This is how the standard deviation works hand in hand with the normal curve. What we needed to know was our data was normally distributed because that's what gave us this picture and the 68, 95, 99 rule that gave us all those percentages. Then we need to know what is the mean so that we knew what to put in the middle. And then what is the standard deviation of this data set so we know what numbers to put in these places. The bigger the standard deviation, the bigger the gaps in these numbers because the more spread out the data set. This is how the mean and standard deviation work together with the normal curve. Now let's answer some questions. The first question we were given here says, what percent of the students scored above 250? So what we're going to do is we're going to go back and look at our picture. We're going to say, okay, well, here's where 250 is, right there. What percent of the students scored above 250? Well, above 250 are the students that are over here. And so what we need to do, if we want to know what percent of students scored above 250, is we need to identify those regions and add all that up. And so we'll say 34 plus 13.5 plus 2.35 plus 0.15 is 50% of the data is to the right of 250. Some of you may have said, well, it's the mean. You told us it was right in the middle, so half the data is above that. You'd be exactly right. But just to sort of illustrate the point of how we're going to use this picture to answer questions, I wanted to go through the individual steps of identify where we are, identify the regions we want to count, and then add those up. And we wind up with 50% scored above 250. Please let me know if you have questions. I'm going to move on to the next one that says, what percent scored below 300? So what percent of the students that took this scored below 300? I'm going to use this picture. Here's where 300 is, at one standard deviation above the mean. The students that scored below 300 are back here. So what I'm doing is I'm adding up all of those. So in order to get that percentage, what I need to do is I need to add up all the percentages that are in the regions that I want to count for this particular question. 34 plus 34 plus 13.5 plus 2.35 plus 0.15 is 84%. 84% of the data is to the left of one standard deviation above the mean. Since 300 was the score I was asked about, and I wanted to know the people who scored less than 300. So it's these people back here that I want to count, and that's 84% of the people that took this test, scored less than 300. Before I keep going, does anybody have any questions about those two? Excellent. I will give you a chance to practice some of these with some polling, but for right now, I just kind of want to get a sense of where we are. Sounds like we're okay. The next question says, what percent scored between 150 and 250? Okay, so I go back and I find, all right, well, let's see. 150 is right here, 2 standard deviations below the mean. 250 is here, that's the mean. And between there is that piece of my diagram, which is these two pieces right here added together, 34 and 13.5, that's 47.5%. So what percent of the students scored between 150 and 250? 47.5% did. Slight change in these next couple of problems. This next one doesn't say what percent. Instead, it says how many. When it says how many, we need to know how many total students there were. So that 2000 is finally going to come into play. Up to now, it hasn't mattered. We had the mean, we had the standard deviation, we had our picture. We could answer any question about percent. Once the question changes to be how many students, then we need to know how many students there were. We're going to start by finding the percent and then answer the question. How many scored above 350? So I'll go back to my picture and I'll find 350. Above 350 is over here. So that's not very many. It's just these two percents added together. 2.35 plus 0.15 is 2.5%. So it's only 2.5% that scored above 350. This says how many, and so what I need to find is 2.5% of the 2,000 students that took the test. So we have to do all the same things we did before. There's just one more step thrown in at the end. I need to find 2.5% of 2,000 to find the actual number. How many? Convert 2.5% to a decimal. Move the decimal point over 2 places, so that's 0.025. And just to sort of check my work there, I'm going to move it 2 places. Okay, yeah, that's right. When it's little bitty numbers like that, it can be hard to make sure you converted to a decimal correctly. So it doesn't hurt to sort of double check. Of is going to be multiply by 2,000. And we find out that 50 students scored above 350. So 2,000 students took this test. Only 50 scored above 350. So somebody who scored above 350 did really, really well. Last question on this page. How many scored under 150? Go back. I'll use the same approach here. I'll find 150. Under 150 is back here. So the parts that I need to add up are these. Hey, that's 2.5% also. Oh yeah, the normal curve is symmetric. If I'm to the right of 2 standard deviations above the mean, and I'm to the left of 2 standard deviations below the mean, it's going to be the same percentage because it's symmetric. So, 2.5% scored under 150, 2.5% of 2,000. Well, that's going to give me the exact same answer I had before. That's also going to be 50. And it's because these two are symmetric to each other. Above 350 and below 150 are symmetric. So they're going to have the same result. Up next, we're going to practice. Before we do that, does anybody have any questions about anything we did on this page? Using the normal curve and standard deviation to answer questions. Excellent. Okay, here goes. 500 students took a standardized test that had a mean of 26 and a standard deviation of 3. What percent scored between 23 and 29? What percent scored above 29? I'm going to set up a poll for this. I'm going to give you some time. Right now, the mean and standard deviation are the most important things for us. Those are how we're going to figure out what our labels are going to be on the bottom of our normal curve. Then we're going to go answer these questions. Like I said, I'll set up a poll. I'll give you some time to answer these 2 questions. And I imagine you're way ahead of me, but your approach here is to sketch a normal curve, put the labels across the bottom, and then use the percentages within each region to answer the questions that we're after. No rush. Keep working through this one. Well, I guess these two. I think we'll go another 30 seconds. If you need more time, let me know. Okay, let's see where we are. Unanimous again. Outstanding. All right, let's take a look at these. If you have questions, please don't hesitate to ask. Maybe you hit the wrong button and got lucky to get it correct. I doubt that's true, but it's not impossible. If you see something you're not sure about where it came from, please let me know. Okay, so what we've got here is a mean of 26 and a standard deviation of 3. I'm going to go back and use my old picture here. Go ahead and clean this off and start fresh. Our mean was 26 and our standard deviation was 3. So that'll be 29, 32, 35. And then on the other side, we'll go down by 3, 23, 20, 17. So I've got my labels in place. Now I'm ready to answer whatever questions have been thrown my way. What percent scored between 23 and 29? So we'll go back and we'll look at our normal curve and we'll identify, let's see, here's 23, here's 29. So we're talking about this part of the graph right there, or picture, I guess. And it's add those two together and that's 68%. This is a straight application of the 68, 95, 99.7 rule. 68% of the data is within one standard deviation of the mean. So for that first question, our answer is 68%. Now for the second question, it says, what percent scored above 29? So we'll go back and we'll take a look at our picture that we've got our labels on, and here's where 29 is, one standard deviation above the mean. If we want above 29, so that's all of this. So what we need to do is add up all of the people who were above 29, and that's 13.5 plus 2.35 plus 0.15, 16%. And so 16% of the people scored above 29. And so our answer to that question then would be 16%. Any questions about anything we did there to answer those two questions? I'm going to have you try a couple more. Okay. 500 students took a standardized test that had a mean of 26 and a standard deviation of 3. So same picture from before. Our two questions here are, what percent scored between 23 and 32? And, important distinction, how many of the students scored above 20? I'll set up a poll for this one and let you try it. You can use the same normal curve that you drew for the last one, so that's good news. Same idea here. We'll use our normal curve. We'll identify the regions where uh, where where the question has pointed us towards. And then once we know those regions, we can figure out what percent are in there or how many are in there. We'll go another 30 seconds and then talk about it. You let me know if you need more time. See where we are on this one? Okay, not unanimous, but there's a easy correction in there that I think we'll be able to make. Okay, so as we look at this one, we still have a mean of 26 and a standard deviation of 3, so we're going to use that same normal curve diagram. And our first question here says, what percent scored between 23 and 32? So we'll go back and take a look. And let's see, between 23 and 32, here's 23 at 1 standard deviation below, and 32 is over here at 2 standard deviations above. So it's this part under the curve that we want to count. So that's what we need to add up. 34 plus 34 plus 13 and a half, and that's 81.5%. And almost everybody was there with the 81.5%, so that's really good. So 81.5% were between 23 and 32. Pretty significant number of the test takers, 81.5%. The second question here said, how many students scored above 20? The first thing we're going to go find is the percent that scored above 20. And to do that, we'll go back to our diagram. We'll find 20 here at 2 standard deviations below the mean, and above 20 then is all of these people. So what we need to add up to get the percentage of students that scored above 20 is all of those. So 13.5 plus 34 plus 34 plus 13.5 plus 2.35 plus 0.15, 97.5%. So 97.5% is the correct percentage. We just have to be a little bit careful that this question didn't ask for the percentage, it asked for how many. So 97.5% of the 500 students that took the exam, that's how many scored above 20. We'll convert that to a decimal. Of is a multiply times 500, and let's see, 0.975 times 500 is 487.5. And since we can't have half of a person that scored there, we're going to round that to the nearest whole number, which means we're going to find the ones place. Look one space to the right, that's 5 or bigger. So we'll round this up and say that 488 students scored above 20. Are there any questions on what we did on either of those two? There were a couple of 97.5 answers, but hopefully we fixed that up, and it's because of the way the question was phrased with how many. Okay, one more normal curve question I want to share with you, and that's making a prediction. For example, a student scored 400 on a standardized test that had a mean of 250 and a standard deviation of 50. What would you expect this student to score on a test that has a mean of 100 and a standard deviation of 10? Now, your first thought here might be, well, how am I supposed to know? Well, there's an assumption we're making here is that the new test is over the same content as the other one, and we expect them to do just as well. So what we're going to do here is we are actually going to go ahead and draw a normal curve for the first test that they took. And that first test had a mean of 250 and a standard deviation of 50. Not the prettiest normal curve ever, but it doesn't have to be. We're just making a sketch. And we know they scored 400. So if we draw this out, that'd be 300, 350, and then 400. And that student's score was here at 400, which is right here, and that's 1, 2, 3 standard deviations above the mean. So on this test, they scored 3 standard deviations above the mean. When we go to make a prediction about the other test, this is going to be the key. They scored 3 standard deviations above the mean on the test they took, so we expect them to score, and that's what the question is. We expect them to score 3 standard deviations above the mean on the other test. And so I'll sketch another normal curve. This one has a mean of 100 and a standard deviation of 10. So that'd be 110, 120, 130. Since they scored 3 standard deviations above the mean last time, we expect them to score 1, 2, 3 standard deviations above the mean this time. So what we would expect them to score on this one would be 130, because that would be 3 standard deviations above the mean. And that's all we're after there. We're not after anything any more complicated than that. If you see a question like that one, what we're doing is we're saying whatever they scored in relation to the mean on the first test, we expect them to have the same performance on the second test.